Hello friends, welcome back in this video session of Extended Surfaces Part 3. My name is Mr. S. V. Kumbar, Assistant Professor, Sharad, Institute of Technology, College of Engineering, Yadra, Ichalkaranji. So, in earlier video lecture, we have studied two derivation. One derivation was based on for infinite length of fin, and second derivation was related to a fin insulated at its tip. So this is third derivation. We will continue with fin of finite length losing heat from its end by convection. Means when the fin tip is there, heat will be directly convected to ambient temperature. So observe this figure. In this figure here, from this end the heat will be directly convected to ambient temperature. So q conduction is equal to q convection at this end, that is minus k dt of dx at x is equal to l is equal to h theta l, as cross sectional area is same for both. A is cancelled here. So here heat conducted to the tip of the fin must be equal to the heat convected away from the tip to ambient temperature, that is from this end, that is at tip. Q conduction is equal to Q convection. Q conduction is written as from Fourier's law minus KAC dt upon dx when x is equal to L, which is equal to HAC TL minus TA. As I said, AC will get cancelled, and minus K dt upon dx at x is equal to L is equal to H, that is convective heat transfer, into theta L, where theta L is this difference TL minus TA. So to determine the temperature distribution, again try to memorize the governing differential equation that we had already derived in first part, that is d2 theta upon dx square minus m square theta, which is equal to 0. So as Ta is the ambient temperature, To is the base temperature, at from this there will be convection, and this is the temperature profile for temperature drop from base temperature to its temperature at its length. Now we will choose its solution for temperature distribution as theta x is equal to A hyperbolic cos mx plus B hyperbolic sin mx, that is 6.2b equation. Now as there are two constant, we will require two boundary conditions. First boundary condition, at x is equal to 0, then t will be equal to t0. Now putting this boundary condition here, so theta x is equal to t0 minus tx, that is theta 0. And second boundary condition, at x is equal to L, heat conducted to the end is equal to heat convected from the end, that is minus KAC d theta of x upon dx when x is equal to L, which is equal to HAC theta L, where theta L is TL minus TA. Now solving this, we will get K is equal to d theta of x upon dx, which is equal to this h is taken here, so plus h theta L is equal to 0. Now try to remember that formulae that I had given, that is K A M hyperbolic sin ml plus B M cos hyperbolic ml plus H A hyperbolic cos ml plus B hyperbolic sin ml, which is equal to 0, using the relation that I had already provided in table. And here we will get A is equal to theta 0 and B is equal to minus theta 0 into bracket hyperbolic sin ml plus h upon mk hyperbolic cos ml divided by hyperbolic cos ml plus h upon mk hyperbolic sin ml. So substituting A and B, we will get theta x upon theta 0, which is equal to hyperbolic cos m L minus x plus h upon mk hyperbolic sin m L minus x divided by hyperbolic cos ml plus h upon mk hyperbolic sin ml, and therefore the heat transfer rate is given as q fin is equal to KAC m theta 0 tan hyperbolic tan ml plus h upon mk divided by 1 plus h upon mk hyperbolic tan ml. So in practice, even when the fin is losing heat from its tip, it is easier to use the equation 6.8 or 6.9 obtained for a fin with insulated tip, but with a corrected length LC rather than actual length. We will include the effect of convection at the tip. That is, in that case only, to evaluate Q, L is replaced by its corrected length LC, and for rectangular fin, corrected length LC is equal to L plus T by 2, where T is the thickness of fin. For cylindrical, that is round fin, pin fin, corrected length L, LC is equal to L plus R by 2. While solving numerical, we will require these basic concepts. Now, up till now, we have derived three different derivations, that is, the heat transferred through an infinite fin, the heat transferred through a fin with its end is insulated, and third, just now we have seen the fin through which the heat is convected from its end. Now, coming to performance of fin. Generally, performance of any device is calculated with the help of its efficiency. Now, what is efficiency? Efficiency in general term is related to output upon input. So, what is the output of this particular object divided by input which is given to that object? Now, fin efficiency is defined as the amount of heat actually transferred by a given fin to the ideal amount of heat that would be transferred if the entire fin were at its best temperature. That is, efficiency of fin is equal to Q fin upon Q maximum. The maximum heat transferred will take place from its best, right? So we will see fin efficiency for these three cases: for an infinitely long fin, for a fin when its tip is insulated, and third, for a fin when its base or when its tip will directly transfer heat through convection. Now we have already derived this equation. For infinitely long fin, actual heat transferred is given as Q fin is equal to square root of HPKAC, which is equal to square root of HPKAC TO minus TA, where TO is the best temperature, TA is the ambient temperature. This is the replacement for theta 0. Now to calculate Q max, the entire fin surface were supposed to be at its best temperature, therefore the heat will transfer by convection from its base. Therefore, Q maximum is equal to HPL into TO minus TA. Now, dividing equation, previous equation, here by this equation, we will get efficiency of fin for an infinite long fin is equal to square root of HPKAC into TO minus TA divided by HPL TO minus TA. TO minus TA will get cancelled. Here HPL, here HPKA. Now try to solve this. We will get efficiency of fin is equal to 1 upon square root of HP upon KA into L. Now we had replaced square root of HP upon KA by M. Here also we will replace. So efficiency for a very long fin, that is infinitely long fin, is given as 1 upon ml, where m is square root of hp upon ka. Similarly, for a fin with insulated end, So there is a presence of hyperbolic tan ml in previous derivation. So q fin is equal to square root of hpka to minus ta hyperbolic tan ml, and similarly fin efficiency is given a denominator will remain same because this is the maximum possible heat transfer through the fin. So efficiency of fin for insulated tip is equal to square root of HPKAC TO minus TA hyperbolic tan ml upon HPL TO minus TA. TO minus TA will get cancelled, and in various and very previous case efficiency of fin is equal to this term will be remain as it is hyperbolic tan ml divided by square root of hp upon ka into L, and here again replace square root of hp upon kac by m. So efficiency for a fin with its insulated tip is given as hyperbolic tan ml upon ml. Now remember, we will require this formulae while solving numericals. These are the efficiency for few fin shapes, where AC is area of cross section, AF is the total fin surface area, LC is the corrected length, P is the perimeter of fin section, H is the heat transfer coefficient, and M is here HP upon KAC, it is square root of HP upon KAC. Now for a straight fin of rectangular cross section, AF is equal to 2WLC, corrected length LC is equal to L plus T by 2, M is equal to square root of HP upon KAT. Now here after solving this we will get square root of 2H upon KT, and its efficiency formula, efficiency is equal to hyperbolic tan MLC upon MLC. Similarly for straight fin, these formulas are listed. Similarly, it is circular fin, that is pin fin with circular cross section, pin fin with rectangular cross section, and pin fin with conical cross section. Now next one is the fin effectiveness. Now fin effectiveness is defined as it is the ratio of heat transfer rate with fin to heat transfer through without fin. If fin is present, then amount of heat transferred, and if fin is not present, so obviously effectiveness should be as large as possible. Means what? If fin is not supposed to present there, what will happen? And if by provision of fin, by how much amount heat will be enhanced, right? So use of fins is hardly justified unless fin effectiveness is greater than 2. Means if the heat transfer rate is doubled, then and then it will be justified. So let us consider this is the base surface when fin is not used. So this is the amount of heat transfer by convection only, and by the presence of fin, that is in the second figure, heat will be conducted through this as well as convected through this. So effectiveness of fin is equal to q fin upon q no fin when fin is present to when fin is not present. So again we will consider those three cases that we have derived derivation. Consider an infinitely long fin, then its effectiveness is given as square root of hp upon kac to minus ta upon hac to minus ta. So this is the fin effectiveness for long fin. After solving this, we will get ef is equal to square root of kp upon hac. Now there are significant conclusion we can made from this derivation. The thermal conductivity K should be as high as possible. That's why we see that generally fins are made up of copper or aluminum, and generally aluminum is preferred over copper because of its cost and weight consideration. Almost in all applications that we have studied in earlier video lecture, the fins are generally made up of aluminum. In PC, laptop, because of weight consideration, because of cost consideration, Generally we prefer aluminum or aluminum alloy as fin material. Second, large ratio of perimeter to cross sectional area is desirable. That means thin, closely spaced fins are preferred. That's why in radiator generally we prefer thin as well as closely spaced fin. However, fins should not be too close to each other because there may be chances of creation of turbulence, right? And third one, fins are justified when heat transfer coefficient H is very small, that is generally on gas side of heat exchanger rather than on liquid side. For example, car radiator has fins on the outside of the tube across which air flows. Therefore, in that case, Hp upon ACS, HACS is greater than 4. Now we will solve few numerical based on this. This is first numerical. So try to read the numerical first. The extent to which the tip condition affects thermal performance of fin depends on the geometry and thermal conductivity as well as convection coefficient. Now consider an alloyed aluminum which its thermal conductivity K is equal to 180 watt per meter Kelvin. Rectangular fin of length L is equal to 10 mm, length is given, thickness T is equal to 1 mm and width is greater than T. The base temperature of fin Tb is 100 degrees centigrade and the fin is exposed to a fluid of temperature 25 degrees centigrade. Now question number 1, assuming a uniform convection coefficient H that is equal to 100 watt per meter square Kelvin over the entire surface, determine the fin heat transfer rate per unit width, efficiency, effectiveness, thermal resistance per width and tip temperature for case A and case B which was given in the table, and contrast your result with those based on infinite fin approximation. Now initially consider an infinitely or insulated tip and just contrast your result with infinite fin approximation. And question B is explore the effect of various in the convection coefficient on the rate for 10 is greater than H or it is less than 1000 watt meter square Kelvin. Also consider the effect of such variation for stainless steel. K is equal to 15 watt per meter Kelvin. Now case 1, fin with insulated tip. Fin with insulated tip, K is given as 180 watt per meter Kelvin. Length is given as 0.01 meter. Its thickness is also given 0.001 meter. Width is 1 meter. So ambient temperature TA is 25 degrees centigrade and base temperature is 100 degrees centigrade. H is also given as 100 watt per meter Kelvin, watt per meter square Kelvin. AC is equal to W into T. So AC is equal to 1 into 10 raised to minus 3 meter square and its perimeter is 2 into W plus T, that is 2.002 meter. Now all these, observing this given data, so m factor for fin is given as square root of Hp K upon AC. Putting the value of H, P, K, AC, we will get m as 33.33. Now Q fin, when fin is insulated, so the formula is KAC m TB minus TA hyperbolic tan ml. So K is given to us, cross sectional area we had already calculated, M we had already calculated, TB TA it is given, M we have calculated, L is also calculated. So substitute all the appropriate values, we will get the amount of heat transferred through fin when its end is insulated as 144.82 watt. Its fin efficiency is given as hyperbolic tan ml upon ml. Substitute all values, we will get its efficiency as 0.965, that is 96.5%, and tip temperature TL is equal to TB minus TA hyperbolic cos ml plus TA. So its tip temperature TL is given as 96.01 degree centigrade. Fin effectiveness is calculated as the amount of heat transferred through insulated tip divided by HAC TB minus TA. So effectiveness of this fin is 19.30 and thermal resistance of fin is TB minus TA upon the amount of heat which is transferred through insulated tip, that is thermal resistance RF is equal to 0.518 degrees centigrade per watt. Case number 2. So this is the case number 2, fin with convection from tip. So Q convected from its tip is equal to KACM TB minus TA into hyperbolic tan ml plus H upon mk divided by 1 plus H upon mk hyperbolic tan ml. Now heat transfer through this fin is given as 151.508 watt. Its fin efficiency is given as efficiency of fin, the amount of heat transferred through convection divided by H upon PL plus AC into TB minus TA. Substitute all the values, we will get its efficiency as 0.961, that is 96.10%. Tip temperature TL is equal to TA plus TB minus TA into 1 upon hyperbolic cos ml plus H upon mk hyperbolic sin ml, and we will get its tip temperature as 95.63 degrees centigrade. Its effectiveness is given as Q fin effectiveness upon HAC TB minus TA. Therefore effectiveness of fin is 20.20 and thermal resistance TB minus TA upon Q fin convected, that is 0.495 degrees centigrade per watt. Case number 3, for infinitely long fin, so it will be given as KAM TB minus TA. Therefore the amount of heat transferred through an infinitely long fin is given as 450.225 watt and its efficiency is given as 1 upon ml. So its efficiency is very long, therefore L is not known here, so its efficiency will be 0. Tip temperature TL will be equal to TA because at its tip the ambient temperature will be there, and fin effectiveness is given as Q long upon HAC TB minus TA. So its effectiveness is 60.03 and its thermal resistance is given as TB minus TA Q of long fin, that is 0.167 centigrade per watt. And this is numerical 2. A very long 25 mm diameter rod K 380 watt per meters degree centigrade extend horizontally from a plane heated wall at 150 degrees centigrade. Temperature of surrounding is 30 degrees centigrade and heat transfer coefficient between surface and rod is 10 watt per meter Kelvin. So determine the rate of heat transfer from the rod, how long the rod should be to be considered as infinite, and draw the temperature profile along the length of rod. Second, compare the temperature distribution in the rod if the material were copper K is equal to 380 watt per meter degree centigrade, aluminum K 200 watt per meter degree centigrade, steel K 55 watt per meter degree centigrade. Other data is same. In the second part, we have to just compare the amount of heat transferred through copper, aluminum, steel, etc. remaining all other parameters same. So this is the diagram for given problem. As it is a circular copper rod, so its diameter is given as 25 mm, convert it in meter 0.025, calculate its area, its thermal conductivity is given as 380, second ambient temperature is given 30, convective heat transfer coefficient H is 10 watt per meter square degree centigrade, its base temperature TO is 150. Its solution, since in the problem it is stated that the fin is very long, we will consider L as infinity. Therefore for a heat transfer rate through an infinite fin is given as, the formula is Q is equal to here square root of HP KAC into TO minus TA, where M is square root of HP upon KAC, P is the perimeter, A is the cross sectional area. So AC is calculated here, P is calculated here, P is pi d, it's a perimeter pi d, right? Now therefore M is equal to square root of HP upon KAC, M is equal to 2.052, and here go on substituting, we will get Q fin is equal to KAC MTO minus TA, therefore Q fin is equal to 45.93 watt. This is the heat loss rate from the fin. Second, length of fin required to consider as infinitely long. So Q fin is equal to KAC M theta naught, that is, which will be equated to a fin with insulated end. Just equate these two and try to find out hyperbolic tan ml, whether it is equivalent to 1. So from this, L is equal to 5 upon M, L is equal to 2.43 meter. This is the length which is required to consider an infinitely long fin, and this is the temperature profile which should be drawn with the help of this temperature distribution. This is drawn with the help of computer. And second part, we have to compare the amount of heat transferred through copper, then aluminum, and then steel. So copper we had already calculated. Now we will calculate by considering aluminum. K of aluminum is 200. So the amount of heat transferred through this Q is equal to Q aluminum is calculated, or first of all calculate L, that is 1.76, and for steel L is equal to 0.927. This is example number 3. Circular aluminum fins of constant rectangular profile are attached to a tube of diameter d is equal to 5 cm. The fin have thickness t is equal to 2 mm, height L is equal to 15 mm, thermal conductivity K is equal to 200 watt per meter degree centigrade, and spacing 8 mm, that is 125 fins per meter length of tube. The tube surface is maintained at an uniform temperature of 180 degrees centigrade, and the fins dissipate heat by convection into the ambient air at Ta is equal to 25 degrees centigrade with heat transfer coefficient H is equal to 50 watt per meter square degree centigrade. Now determine the net heat transfer per meter length. So what is given? Diameter is given, length is given, that is radius is given, thickness is given, K is given, ambient temperature is given, its base temperature is given, H is given, and number of fins are given. Now how to start this problem? Let us find M, H P upon KAC, but here P is equal to AC, that is 2 by T. Substitute that value, we will get M is equal to 15.81. Now fin efficiency can be calculated by this formula, just modification of earlier rectangular cross section area, or you can adopt as usual method, right? In the present case, M is equal to 15.81, R1 is equal to 0.025, R2 is equal to 0.041. Therefore, its efficiency is given as 0.973, that is 97.3, right? And total surface efficiency is 1 minus NAF upon AT, 1 minus efficiency of one fin, that is 97.3, which is already calculated. Surface area of fin can be calculated by 2 pi R2C square minus R1 square, that is surface area is 6.635 into 10 raised to minus 3 meter square, and its surface area is 2 pi R1 1 minus NT, that is its perimeter is calculated as 0.118 meter square. Therefore total area is AP plus N into AF, therefore AT is equal to 0.947 meter square. Therefore its efficiency is 0.97, that is 97.6%, and heat transfer rate from the fin is given as Q is equal to HA, efficiency of fin, into its total area TO minus TA. So Q is equal to 7.167 into 10 raised to 3 watt per meter, that is 7.167 kilowatt per meter. So heat transfer rate if there are no fins. So it is interesting to compare the heat transfer rate obtained above with the heat transfer rate that would be obtained if there were no fin. If there are no fin, heat transfer will be through convection only. So applying that law, we will get Q tube is equal to HATO minus TA, where A is circumferential area of fin. So Q tube is equal to 1.217 into 10 raised to 3. So its effectiveness Q upon Q tube is equal to 5.88. Now that is heat transfer increases nearly 6 times because of addition of fin. As we had already discussed, if heat transfer increases by 2 times, then and then just fin can be justified. So thank you very much.